In our previous classes, we have discussed about field. A field is a commutative ring with unity where every non-zero elements form a group under multiplication. That means every non-zero element has a inverse with respect to multiplication. Of course, the field has no proper zero divisors and also no proper ideals. Now we shall discuss field theory, that is the subject of unit 4. So for this one we shall discuss with the field, subfield, and what are the criteria for the subfield and all those things. So a field has at least two elements, 0 and 1. One is called as the unity of the field F. So we shall talk about subfield. A non-void subset S of a field F is said to be subfield of F if for every AB contained in S, for any two elements AB contained in S, A plus B must be contained in S, that is closed with respect to addition. A into B contained in S, that is closed with respect to multiplication. And the second condition is S must be a field under the induced addition and multiplication compositions. So here what happens? A subfield is nothing but a non-void containing at least two elements subset of the field F, which is closed with respect to addition, closed with respect to multiplication, and S itself is a field under the induced addition and multiplication. So let us consider few examples. In the set of complex numbers, R is the set of real numbers. R is a subfield of C. And in the set of real numbers, Q, the set of rational numbers, is a subfield of C. Similarly, these are proper subfields because every field F is itself a subfield of F. So, the field F is called as non-trivial or improper subfield of F. So, any subset having at least two elements which is a proper subset of the field and the subset itself is a field is called as proper subfield of F. So, in the set of complex numbers, the set of real numbers R is a subfield, proper subfield of C, and in the set of real numbers, the set of rationals Q is a subfield of R. Clearly, Q is also a subfield of C. You can verify the result, but we shall use one criteria, very important criteria, that decides a subset to be a subfield of F. So the theorem says any subset S of a field F is a subfield of F if and only if for any AB contained in S, A minus B must be contained in S, and second one is A contained in S and B contained in S implies AB inverse is contained in S and B is not equals to 0. That is another one point because a non-zero element has the inverse with respect to multiplication. What it implies? A non-void subset containing at least two elements, it must be a additive subgroup of the field F. That is, for any AB contained in S, A minus B must be contained in S. Second condition is all the non-zero elements. Here you note that B is not equals to 0. All the non-zero elements in the subset must form a subgroup under multiplication. So, a non-void subset containing at least two elements is a subfield of F if all the elements form a additive subgroup and all non-zero elements form a multiplicative group. So these can be proved very easily. So another one theorem, we shall see that intersection of any two subfields or intersection of any finite number of subfields is again a subfield of F. You note that a field has no proper ideals, no proper zero divisors. So subfield has also no proper zero divisors and no proper ideals. But we shall discuss another one theorem where the theorem says a field F is said to be a prime field. A field F is said to be a prime field if it has no proper subfields. The field, if it has no proper subfields, it is called as a prime field. So we shall discuss the proof of this in the next class.